Hi everyone, welcome to the first module of AI Lit. The learning objectives of this module include gaining a better understanding of artificial intelligence, understanding the use of machine learning and deep learning, understanding how a convolutional neural network works, learning how computer vision is applied to solve real-world problems, addressing AI bias, and learning various applications of AI specifically in agriculture. So first we want to start off with a fun game. As you can see on the screen, there are two images of a tomato plant. One is AI generated and one is taken from Google Images, and it's a real photo that's been taken. We want you to guess which one is AI and which one is real. So we'll give you a few seconds. Okay, so looking at the answers, the one on the left is AI generated while the one on the right is real. And this just exemplifies how amazing and how complex AI is that it's even hard for us to now, with new technology, detect what is AI and what is real. So let's first start off with discussing what is artificial intelligence, or AI. AI refers to technology that allows computers and machines to simulate human intelligence and their methods of problem solving. AI technology can process large amounts of data and recognize complex patterns, performing tasks that would otherwise require human intervention. Digital assistants and AI generative tools such as OpenAI's ChatGPT are just a few examples of how AI integrates in our daily lives. AI also encompasses machine learning and deep learning. These disciplines refer to the development of algorithms that are designed based on the decision-making processes of humans, with an ability to learn from available data and increase their prediction accuracy over time. So now let's get more into machine learning and deep learning. Machine learning and deep learning are specialized branches within the field of AI, with deep learning being a subset of machine learning. Machine learning is a broader concept that refers to algorithms and statistical models that enable computers to perform specific tasks without explicit instructions. Instead, they rely on patterns and inferences. On the other hand, deep learning is a subset of machine learning that uses neural networks with many layers, hence the term deep. Deep learning models are designed to automatically learn with high-level features from data in a hierarchical manner, which is particularly useful for tasks like image recognition, speech recognition, and natural language processing. Deep learning requires a substantial amount of data to perform well because these models learn directly from the data, adjusting themselves to improve accuracy over time without human intervention in feature selection. Now, we want to go into specifically what a neural network is, as this will be the focus of our modules from going forward. A neural network is a subset of machine learning and employs deep learning algorithms to process data, primarily images. They consist of various layers of nodes or neurons, including an input layer, several hidden layers, and an output layer. Each node is connected to others and equipped with an associated weight and threshold. A node is activated and it then forwards data to the subsequent layer if its output exceeds a certain threshold. If not, it does not transmit the data any further. So this is an animation of what it looks like with all the nodes interconnected with each other in a regular neural network. Specifically, let's go into convolutional neural networks. So convolutional neural networks work differently because they are a specialized version of neural networks. They treat data as spatial, and that's the most important distinction. Instead of neurons being connected to every neuron in the previous layer, they are only connected to neurons close to it, and each neuron has the same exact weight. The simplification in the network allows it to uphold the spatial aspect of the dataset. Convolutional itself refers to the filtering process. This network is able to simplify complex images more easily to be understood. So here again is an animation of convolutional neural networks. A CNN is specially composed of multiple layers that process and transform the input to produce a desired output. These layers include the convolutional layers, and these are the core building blocks of a CNN. They apply a set of filters to the input to create feature maps. These filters help the network focus on specific spatial features like edges, textures, and shapes. Then we have the pooling layer. These layers help reduce the dimensionality of each feature map while retaining the most important information. Basically, pooling helps make the detection of features invariant to scale and orientation changes, in turn simplifying it so that it can be more easily understood. Then we have the rectified linear unit, or the ReLU layer. This layer applies a nonlinear activation function, such as the ReLU function, to increase the nonlinear properties of decision functions and of the overall network without affecting the receptive fields of the convolutional layer. Then we have the fully connected layers. So after several convolutional and pooling layers, the high-level reasoning in the neural network is done through fully connected layers. Neurons in a fully connected layer have full connections to all activations in the previous layer, as seen in regular artificial neural networks. The output from the fully connected layers is used to make predictions or classifications based on the input data. In this animation, we see that the CNN is able to detect that the input image that we had put into the CNN is actually corn, and it is able to output this information. So here we can see that the image of the corn becomes further and further simplified by the CNN, so it can be read better and put into a format that can be read by the machine. CNNs are frequently chosen for tasks in classification and computer vision. These networks offer a more efficient method for image classification and object recognition by applying concepts from linear algebra such as matrix multiplication to detect patterns in images. CNNs are especially effective for tasks such as image recognition because they capture the spatial dependencies in visual data, as we had previously mentioned. Their ability to learn feature representations directly from images without the need for manual feature extraction makes them a powerful tool for many computer vision applications. CNNs can be resource extensive, often necessitating the use of graphical processing units or GPUs for model training, which we will go into in future modules. So now let's go into computer vision, as we mentioned that CNNs tend to employ this. Computer vision is a type of AI technology that uses machine learning and neural networks to derive meaningful information from digital images and other visual inputs and make subsequent decisions based on the information. So this would be used in that final connective layer, as we showed, where it detected that the image was corn. Here is an example of what a self-driving car would look like using computer vision and what the car would actually see with this technology. So you can see that it's able to actually look at the images and identify what they represent. Essentially, computer vision involves teaching machines to see and interpret the world in the way that humans do. The process includes several key tasks such as image recognition, which is identifying objects in an image, object detection, which locates the objects within an image, segmentation, which divides the image into segments to simplify its analysis, and classification, which assigns categories to objects in an image. Computer vision relies on pattern recognition and deep learning models to accurately identify and classify objects, and can use vast amounts of labeled training data to learn visual patterns that are associated with different categories of objects. At its core, computer vision seeks to replicate the complexity of human visual systems, enabling computers to see and interpret visuals with high accuracy. So now we want to be completely transparent with our modules and with our model itself. So we thought that in our first introduction module, we would discuss biases associated with AI. Although AI is completely useful and has so many different applications in various scientific disciplines, there can be a bias associated with its design. AI bias describes the tendency of AI systems to generate outcomes that mirror and reinforce existing human biases in society, including both historical and contemporary social disparities. This can stem from the initial data that is used to train the model, the design of the algorithm, or the predictions made by the algorithm. AI systems develop decision-making abilities from the data that they are trained on, making it essential to analyze training data sets for biases. One approach would be to examine how groups are represented in the data to identify over or underrepresentation. Utilizing imperfect training data can then lead to algorithms that consistently generate mistakes, biased results, or exacerbate existing biases in data. For example, in healthcare, underrepresented data of women or minority groups can skew predictive AI algorithms, and computer-aided diagnosis systems have been found to return lower accuracy results for Black patients than white patients. This is just one example of how AI bias can influence the output of its design. AI governance is vital to addressing bias in AI, establishing policies, practices, and frameworks to ensure the responsible development and utilization of AI technologies across organizations. It encompasses compliance with legal standards, fostering trust through data protection, and ensuring transparency to avoid biased data usage. Now let's go into the various applications of AI. AI is revolutionizing the agricultural sector, offering innovative solutions to enhance efficiency, sustainability, and productivity. By integrating AI technologies, agriculture can address some of the most pressing challenges it faces, including resource management, climate change impacts, and increasing demand for food due to global population growth. The general applications of AI in agriculture include its ability to significantly improve decision-making processes in agriculture through precision farming, where data-driven insights help farmers understand the complex dynamics of their fields. AI-driven analytics can predict weather patterns, optimize planting schedules, and recommend crop rotation, minimizing waste and ensuring optimal resource use. Drones and satellite imagery powered by AI algorithms can monitor crop and soil health over vast areas, providing farmers with detailed maps for target action, such as precise pesticide and fertilizer application. Moreover, AI can automate labor-intensive tasks such as weeding and harvesting with robots that work alongside humans, reducing labor costs and increasing the overall efficiency. Now, let's go into our main topic, which is monitoring crop health and increasing yield using AI. Specifically, AI technologies are pivotal in monitoring crop health and increasing agricultural yields, which is crucial in the context of growing food insecurity. Advanced image recognition and machine learning models can analyze images captured by drones or in field sensors to detect early signs of disease, pest infestations, or nutritional deficiencies. These technologies enable farmers to take swift, targeted action to mitigate issues before they escalate, which can preserve overall crop health and optimize yield. AI algorithms can process vast amounts of data from various sources to predict crop performance under different conditions. This predictive capability allows for more informed decision-making, reducing the risk of crop failure and contributing to a more stable food prediction system. In the fight against food insecurity, AI-driven agricultural practices offer a way to increase productivity sustainably. By optimizing resource use and reducing dependence on chemical inputs, AI can help support environmental sustainability and enhance food security. So as we can see that taking in many images of various crops in a field, it can analyze the data using AI technology and process whether the plants are healthy or diseased, which can help inform farmers' practices and increase overall yield. So that is it for the first module. We hope that you learned a lot about AI and its various applications, as well as the subsets of AI technology that can be involved in models that can in turn be used in many sectors, such as the agricultural sector.